Academy podcast with Phil Zito, episode 473. Hey folks, Phil Zito here, and welcome to episode 473 of the Smart Buildings Academy podcast. In this episode, we are going to be continuing our series on control sequences. We're going to be talking about the built-up air handling units. So we're going to be talking about single path. We're going to be talking about multi-path. We're going to be talking about 100% outdoor air, mixed air. We're going to be talking about makeup air units. So we're going to dive pretty deep into the airside systems in this episode. As always, everything is available at podcast.smartbuildingsacademy.com/473. Once again, that's podcast.smartbuildingsacademy.com/473. And if you could do me a huge favor, if you are watching this on YouTube and you find this to be valuable, please hit the like button, the subscribe button. And if you feel so inclined, hit the comment button and reply and ask your questions. We respond to all questions. If you're watching this on LinkedIn, please consider hitting the share button and adding a little blurb about this episode. And if you're watching this on Spotify or Apple Podcasts, please consider giving us a review and subscribing. That really helps spread the podcast. We do this free for you every single week, and that helps the reach of the podcast. As I mentioned, everything will be available at podcast.smartbuildingsacademy.com/473. Let's get into the episode. So far on our podcast journey here, we talked about space control, and we talked about the different variables we control within the space. Then from there, we moved into fan coil units and rooftop units, which are more unitary systems, meaning they typically will be self-enclosed, essentially, controlling their own cooling, their own heating, and typically controlling to a single space. From here, we're now moving into air handling systems. Now, these systems tend to serve multiple zones, and how they do that is either by providing constant volume to these zones or spaces, and then varying the discharge air temperature, or by providing a constant discharge air temperature and then varying the airflow, as we saw in the first episode of this series on VAV boxes. So let's take a look at this single path rooftop unit or air handling unit, constant volume. It's going to take me a little bit to get back into the swing of things. So if I'm a little off kilter from my normal podcast production quality, that's why. I'm simply recovering from 8 days in Disney World with my children, which if any of you have ever done that before, know exactly how exhausting that can be. So with that being said, let's take a look at these little sequences right here. So single zone VAV, constant volume. All right, so whenever we are working with a constant volume system, and I don't even know why they're calling the sequence VAV, technically it should be CAV, constant air volume unit, but whenever we are looking at a single path air handler, whether it be a variable air volume air handler, whether it be 100% outdoor air unit, whether it be a makeup air unit, we're going to run into some common safeties. The most common of those are going to be fan safeties, and they are going to be smoke control safeties. So how this is going to work, I'm going to talk through some of the points. I'm going to talk through some of the things we're going to see in the systems, and then so that's what you can expect. So our primary thing with air handling units is moving the air volume, because that is how we are going to change temperature and humidity. Remember, our primary variable in all airside control is airflow. A lot of folks will say it's temperature. A lot of folks will say it's humidity. Some folks will even say it's CO2, but none of that matters if we aren't flowing air. I mean, you can control temperature to the nth degree, but if you can't get the air into the space, none of that matters. So for those of you who are troubleshooting or programming, you really got to have your airflow down, because if you don't have that, you cannot change the environmental quality of a space. I really want that to sink in. I see a lot of folks who will spend a lot of time troubleshooting temperature and humidity and not look at airflow and be like, hey, I can't control the space. Well, the space is designed for 1,000 CFM and you're giving it 500 CFM. Well, of course you're not going to control the space. It's not going to happen. So a single path air handler constant volume is going to have fan safeties, just like a actual air handler VAV. And this throws a lot of people because people are like, why do we have high static and low static for a fan if it's a constant volume fan? Well, that's because downstream effects on that system can affect the fan and cause overpressurization or underpressurization issues. Overpressurization is where there's some form of blockage, maybe from smoke dampers, or maybe someone commanded all the constant air volume VAVs closed or something. And because of that, we are now seeing that this fan is starting to get too much static pressure on its supply side of the, or discharge side rather, of the fan, and that causes overpressurization, and you should have a high static pressure switch that will trip and will break the fan control circuit. When I say break the circuit, I'm talking about you're running a control signal through this high static, and it's typically a normally closed, and if that triggers, it's going to open up, and that's going to cause the fan to turn off. And it's the same for low static as well, basically the exact same wiring. In addition to this, we'll typically have low temp alarms and we'll typically have smoke alarms. Low temp being that we don't want to freeze any coils, and so we'll go and shut dampers, open up return air dampers, because remember, on single path mixed air handlers, not 100% outdoor air, but mixed air, we can close off the outdoor air damper and open up the return air damper and still maintain enough airflow in order to properly run the unit. So we've got those safeties, and then we have smoke safeties and fire alarm safeties, which are typically secondary monitoring. Those safeties will typically report back to the fire alarm panel, and we will typically have an auxiliary output off of that sensor or an auxiliary contact that we are running our wires through for our safety circuit. By the way, that's what these things are called. We call it a safety circuit, and you often see it on controls diagrams where the actual design submittal will have all of these different coils and or contacts that are going to be energized by safeties, and you're going to see your control signal passing through that. Now, when we're dealing with single path constant air volume, we are really focused on manipulating discharge air temperature, typically off of a reset. Sometimes we're using a trim and response. Sometimes we're just using a average of space, and we're throwing out any wonky values of space temp. Space is 95 degrees or 140 degrees. Well, obviously space is probably not going to be 140 degrees. It's probably a wonky sensor. We're going to throw that out. And so what we'll do is we'll average the space temp, and then we'll reset discharge air temp. And that is how we control discharge air temp for the spaces. We essentially are doing a demand-based reset. That's what it's called. Now, we utilize this because when we're using constant air volume systems, we're not going typically for 55 degrees and hitting saturation and then allowing the air to mix once it actually gets to space. We want to go and provide a constant volume of air, and we are hoping to control discharge air and sometimes even humidity at a constant volume unit. So we're focused in on that. When we're dealing with these type of units, we'll typically have cooling and we'll typically have reheat. Sometimes we will not see reheat at a mixed air single path variable air volume air handler because we will depend on the terminal units downstream to do reheat at the space and zone level. But when we're dealing with a single path constant air volume unit, we are typically, as I mentioned, varying our discharge air based on space reset. And so we typically will have some form of reheat as well. And that reheat will typically be used both for dehumidification sequences as well as just for controlling discharge air. And like I said, we'll talk about those sequences in a second. We also typically will have cooling valves, and we'll typically have low limit sequencing, and we'll talk about that in a second. And finally, we will have outdoor air dampers and return air dampers as well, typically controlling the economizer as well as potentially CO2 and controlling CO2 either via a CO2 sensor or controlling it via just using our ASHRAE 62.1 settings. which once again, we're going to talk about in just a second. There's a lot in this episode. Okay, so let's take a look at the sequence. So the sequence right here, temperature sensor will determine if the unit is in heating, cooling, or ventilation mode during occupied operation. I told you this episode might be a little wonky as I get back in the swing of things. So occupied operation will be determined via several different things: a occupancy schedule, forced occupancy override, push button override on the space sensor, an external scheduling device, etc., etc. And what we're going to do here is we typically will have three kind of modes as far as occupancy goes. We'll have unoccupied, occupied, and off. And there's an important reason we have off. If you are doing maintenance, sometimes you call it maintenance, you don't want to have it in unoccupied. You want to have it off. And that's really important because of unacknowledged alarms and all sorts of effects it may have on other sequences. I really recommend, if you're programming any HVAC system, that you have some form of maintenance mode where basically you disable alarms. That way folks can work on the system and not be triggering the slew alarms and causing all sorts of issues. Okay, so we've got that. We've got our three occupancy modes, right? And within our occupancy mode of occupied, we have heating, cooling, and ventilation. Let's take a look at these. So cooling mode, pretty straightforward, right? We are going to have cooling being enabled by a enable set point, and it's going to say, hey, once our discharge air temp set point is X and we've gone above it by Y, that indicates a need for cooling. Cooling mode's enabled, and then the cooling mode sequence is going to start to operate. We're either going to turn on compressors or cooling coils and open those up and control to our supply or discharge air temp, whatever it's called. Now, if it is compressors instead of coils, coils are straightforward, right? You use a PID loop, you set your integral and your proportional gain so that it properly controls, and then you control the output to the cooling valve. Now, if it is a compressor, if it's, you're using DX cooling, then you're going to take your PID output and feed that into a sequencer block. Now, some programming will allow you to directly control to a sequencer block. I personally prefer being able to control via a PID loop and then feeding into a sequencer block, which uses min and max times. Now, there's pros and cons to this, right? So if you're using a PID loop and you're feeding into a sequencer block, the cons of that are that your PID loop, if it's self-tuning, can get a little bit out of whack because of the min and on and offs and your minimum runtimes and maximum runtimes of your sequencer block, which means your stages of your compressors can stay on for a certain amount of time, and the PID loop may be calling it to be off, and it's like, what the heck, and it spins up or winds down, and you get some issues. On the flip side, if you use a sequencer block, what can happen is that you will not have granularity of control. Once you hit that 50% threshold, that sequencer block is going to come on. Now, there's a variety of different ways. I don't want to get too much into the sequence of programming here, but either one works. PID into a sequencer block or just directly controlling into a sequencer block. For some of you who are like, what the heck did Phil just talk about? That makes no sense. I encourage you to go check out our ultimate guide to BAS programming, where it talks through sequencer blocks and PID loops and things like that. And I'll provide a link to that at buildingautomationmonthly.com/185. All right, continuing along. Now we move into heating mode. So we drop below discharge air set point. We are not, we're getting too cold, right? We're discharging cold air, and that's not good. We don't want our spaces to get too cold. So the first thing that would happen is our space reset, right? We would see our spaces getting cold. It would reset our discharge air temp up. And what's going to happen is eventually we're going to stay below discharge air temp set point, and we're going to have to turn on heat. And this is where we start to turn on a variety of different heat types, either gas heat or hot water heat or electric heat or SCR heat. There's a variety of different types of heat we can turn on. The important thing to realize is, am I controlling via PID loop my heat? So am I controlling, SCR, which basically is staged electrical heat is what it is. You take a 0 to 10 volt signal and it stages on electric heat. Or am I controlling a gas command with a Boolean output or electric heat with a Boolean output? And in that case, you're just looking at a simple comparator. If I'm above X, I turn on Y. So from there, right, we have our heat, and that's all well and good. We've got heat, we've got cooling, but then we have this thing called ventilation. What is the purpose of that? Well, sometimes you've met your set point. Set point's great, right? You're hitting 65-degree discharge air, you're using Economizer, everything's all well and good, but you still need airflow, and that is where ventilation mode comes in, and it simply circulates airflow in order to provide airflow to the space as needed, or spaces as needed. So it's important to realize that when you're in cooling, or not in cooling mode and not in heating mode, you still want to have ventilation mode going, because if you don't have ventilation, if you don't have airflow, then you're not going to satisfy ASHRAE 62.1, the space air is going to get stagnant, people are going to start to get tired. You can actually get people quite sick if you aren't removing CO2 and things like that, depending on your building envelope and how well sealed it is and how well your pressurization strategy goes. You can actually essentially fill a space with really bad air, because remember, at the end of the day, air, just like water, has mass and volume and will fill a space. Air is actually an object, and a lot of folks, they don't realize this. They think, oh, water, obviously an object, right? Steam, obviously an object. It has mass, right? But then air has mass. I mean, much less dense than water, but it still has mass, and it can fill up a space. And so we need to make sure that we have air flowing constantly in order to keep an optimal environment for our occupants. So from there, we have, and I slightly mentioned it, we have this Economizer mode. Now, when we talk about Economizer, we have various different ways of controlling Economizer, but in a nutshell, Economizer serves two purposes. Economizer serves a free cooling purpose, which is if our space or our outdoor air is at a certain point, either via temperature or via temperature and humidity, enthalpy, if we are looking at the temperature of the air, or we're looking at the energy in the air, which is moisture content, which I'm going to take a brief segue to talk about that, because there's a lot of folks who don't understand psychrometrics, and they don't understand moisture content in air, and they don't understand what that means. So I really want to go down that path with you real quick. And the reason why is, oftentimes folks will, when they're new to this field, they'll say, oh, Economizer, it's 65 degrees outside, I'm going to control with the Economizer. It's great, awesome, free cooling. And then they don't look at like 65, 90% humidity. I know those are some crazy wonky numbers, but what you have to realize is as temperature increases, the effect of relative humidity is massive. So the amount of moisture, grains of moisture per pound of air, at 55 degrees with 100% relative humidity is completely different than 90 degrees and 90% relative humidity. So as air gets hotter, it can store more moisture in it. And so 90 degrees with 90% relative humidity is a much larger amount of moisture. And moisture, the problem with it is, one, it impacts the ability for the evaporation effect. When you're blowing air across a human body, you have the evaporative effect, and the evaporative effect removes moisture off the skin of the body, which causes people to feel cool, which is also a reason why you start to dry out if the humidity level is too low and your skin starts to chap, because too much moisture is being removed from your body. So ideally, we're in the 50 to 60% relative humidity range to kind of maximize that evaporative effect. The problem is when we introduce 90% relative humidity at hot temperatures, that is a ton of moisture that has to be removed by the system. And the only way the system, the air handling system, can remove moisture is to bring the temperature to saturation, which basically means that we cool the temperature down to the point where as temperature lowers, it has less capability of holding moisture. So as the temperature gets lower, what's going to happen is that moisture is going to condense and leave the airstream. It has to, because it can simply no longer be held and contained by that air at a colder temperature. So when we're dealing with Economizer, what happens here is a lot of folks will initially focus on what's called dry bulb temperature, which does not account for humidity. And that's all well and good in some climates, but if you're in, the deep south of the US, that's not good because there's a lot of humidity. And with that humidity, you are introducing moisture into the system that cannot be removed by the system, which starts to heat up and make the spaces feel muggy. So when we're dealing with Economizer control, typically we're going to look at dry bulb, which is just pure outdoor air temperature, and we're going to have an enable set point. And then we're going to let Economizer control the discharge air temp. And if it doesn't meet discharge air temp, we're going to shut it back down to minimum position and start to enable the cooling coil. With some systems, we'll actually look at enthalpy, which factors in the relative humidity of the air and the moisture content of the air. And by doing that, we'll make a decision: is the return airstream more humid and more moist than the outdoor airstream? And if it is, then we're going to close down that return airstream and we're going to utilize the outdoor airstream, because the mechanical effort of our system to remove that moisture is going to be lessened by making that calculation. So that's for Economizer control for a cooling scenario. And I'm looking at the time here and realizing that we're probably not even going to get into mixed air units of variable air volume. I just think we're going to run out of time, but we'll try. All right, so what also we have, though, is CO2 control. And so ASHRAE 62.1 defines, based on space type and occupancy count, you must have a certain amount of fresh air within a space, and that's required. Now, what we learn with Economizer control is that we can utilize a CO2 sensor, and we can measure return air or space CO2, and we can measure that and then control our Economizer position in order to control the CO2 level of the space or the return airstream. Now, what we also learn is that utilizing that control, we can also just simply have a pre-programmed, and this works really well on constant air volume systems. It's a little wonky on variable air volume systems. But on constant air volume systems, where the air volume is constant, the fan's at a constant speed, we can set a minimum damper position for our CO2 and ASHRAE 62.1 control, because we always know how much air we're going to be pulling in via the airstream because we have a constant volume of air. When we're using variable air volume systems, that's where things get a little weird, and that's why we tend to have to use airflow stations in order to properly control. I mean, anyone who's telling you that you're using a variable air volume air handler, and just by putting 10% at the minimum outdoor air damper position, you're actually controlling to ASHRAE 62.1 is really not giving you proper information, because as you start to vary the speed of the air being drawn by those fans, you actually are affecting the amount of air that's going to be coming through those dampers and the mixture accordingly. All right, so with that being said, that kind of takes us through this constant air volume air handler. Let's now look at the variable air volume, because there's really not too much different, and I think we have enough time. We're at 24 minutes. So the real big difference here of a variable air volume system is utilizing a VSD or VFD. So a VSD varies the speed of the fan, whereas a VFD varies the frequency of the electrical signal, and that's how it controls the speed of the fan. So essentially different ways of controlling a fan, but achieving the same thing, which is modulating the air volume being provided to control to a discharge air pressure set point. Now, this discharge air pressure set point is anywhere between 1 to 3 inches water column. That's how we measure discharge air pressure. And how that discharge air pressure is affected is when VAV boxes downstream from this VAV air handling unit close or open up, that causes the discharge air pressure of the duct to change. And what will happen is that the air handler will be monitoring the discharge air pressure and discharge air pressure set point, and will vary the fan speed accordingly in order to basically provide the proper amount of air volume to these VAV units. Now, there's a couple little nuances here. Some folks will look at average damper position and will simply do a reset of a range of discharge air pressure set point. That can work in some cases. If you have constantly varying space dampers, you can have some issues in that can start to really cause some oscillation of your PID loop, and PID loops for fans are very responsive because of the effect of fan speed on discharge air. The effect of the output of a fan on the process variable, which is discharge air pressure, is really, really quick. It's almost an immediate effect. It's very interesting to watch. It's kind of like watching steam. When you start to open up a steam valve, you have an almost immediate effect on discharge air temp. And it's the same with fan speed and air volume and discharge air pressure. Now, one of the things that folks will do is actually a trim and response sequence. Now, trim and response is where you're going to look at the average zone, call for heating or call for air, and or damper position. And what will happen is you will either respond to that by increasing the discharge air pressure set point, or you will trim that by reducing the discharge air pressure set point. And this control is fairly common in advanced ASHRAE sequences. It's not something I particularly like because it makes it difficult to troubleshoot. And honestly, I've seen more folks mess it up than get it right. And I think most folks would be better just picking a static discharge air pressure set point, especially here in the US where utility costs are so low. I know that this slightly, not doing a reset sequence, slightly increases the wear and tear on the equipment and increases the utility cost of the equipment. But here in the US, we can afford that. Overseas, maybe not so much. But I will tell you, I've seen more problems with reset sequences than I have seen with actual, what's the word I'm looking for? Static discharge air pressure set points. Hey, folks, I hope you enjoyed this episode. I hope it was informative to you. As always, if you have any questions, do not hesitate to reach out to us either on YouTube, LinkedIn, Facebook, or in the comments of our website at podcast.smartbuildingsacademy.com/473. Everything we mentioned in this episode, you'll be able to find at podcast.smartbuildingsacademy.com/473. You will also be able to find a link to our free skill assessment. If you're trying to figure out what you know or what others know, I highly encourage you to go to smartbuildingsacademy.com/skills and take our free skill assessment, the only skill assessment trusted by over 24,000 people to test and quantifiably measure their skills in building automation. Thanks, everybody.